So we're continuing what we did yesterday, looking at the idea of a derivative. In this case, it's the idea of a derivative at a point. And I mentioned the word derivative came up 200-300 years ago because this instantaneous rate of change was kind of a paradox. So they needed another way to talk about it that kind of skirted the paradox. And we're deriving this change function out of a given function. So we're going to look at a couple of examples. So let's look at some movement right now. On a straight line. So we're watching this thing move, and it moves at not in a it's moving on a line, but it's like kind of speeding up, slowing down, backing up, things like that. And so the expression we're going to use for its movement is S, is a common term for a common letter for displacement in physics type situation. It comes from the Greek, which stands for like space between things. And we're going to say it is t squared minus 2t describes the movement on the path. And what we want to do here is we want to find the average velocity from t equals 2 to t equals 2 plus h, and h is just some random jump, not random, but arbitrary small jump in time there. So that's going to be step A of this problem, and then step B in this problem, we're just going to play around with some different h's. And so we'll try a pattern of h's, a geometric pattern where h is going to be 1/10, and then 1/100th, and then 1,000th. And then we want to do is see if based on that, we can then estimate the instantaneous rate of change. So that's what we're going to do. To do average velocity, right, so part A here, our formula for average velocity is f of whatever number we're looking at. Oops, I did that backwards, y2, so 2 plus h, which is the little jump, minus f of h divided by h. So that's average velocity. And this function f is really s. And there's a couple ways to deal with this. If you look at the examples of the book, they just plug the function right into this formula and you get this big, giant fraction. I don't typically like to do that. I like to break it down and do it in pieces. So my advice is if you ever have trouble with the algebra here, is to think of the function without a t or an x in it, and just rewrite it with empty parentheses instead of the t or the x, whatever variable we're using for the independent. So I can view my function like this, and then whatever I'm told to put here, I just put there and there. Right? And so the hardest part, I think, here of this problem is plugging in the 2 plus h in all the different spots and making sure that goes right. So I like to just isolate that, do it first, and then go into the fraction. So remember, squaring something means multiply it by itself. There's no shortcut for that. And so that's going to be 2 plus h times 2 plus h. And so that's going to give me 4 plus a 2h and another 2h. So that's going to be 4 h's plus h times h, or h squared. And then minus 2 times 2 and minus 2 times h. And I think that looks okay. So then finishing that up, what do we get? The 4's subtract themselves out of existence. That's kind of nice. Then we have 4h minus 2h. So we have 2h plus h squared, which you can reverse the order if you wish, but that's fine. So then looking back at our difference quotient here, our average rate of change, we then have to subtract s of, ooh, that should be a 2 there. S of 2. And so from that, we're going to subtract s of 2 And so S of 2 is going to be what? 2 squared minus 2 times 2. So what's that? 4 minus 4 is 0. Well, that's convenient. Cool. So now we have our numerator of our fraction. So again, our difference quotient, our average rate of change, S of 2 plus H minus S of 2 all over H gives us 2H plus H squared for the numerator divided by H. And that's kind of nice because the H's are going to divide out here and here. And so that's going to give us 2 plus H. All right, and this is similar to a problem we did the other day. A little algebra tips from here to here. If this were on a test, I would write a little bit more work. I would probably have an intermediate step of 2 factoring out, not the 2, the H in the numerator, and then saying, oh yeah, a number divided by itself is 1, and there's my 2 plus H. So that's part A. Part B said plug in a couple values of H. So for part B, I'm going to make a table here. Spreadsheet would be kind of cute here. So we have values of H, and then we have our average rate of change. Well, that's cool. Arc. I never wrote that down before. 0.1 for H, 0.01, 0.001. So a tenth, hundredth, a thousandth. Well, so that's pretty straightforward here. It's just 2 plus whatever that is. So the should be 2.1 and 2.01 and 2.001. And as H gets small here, right, approaches 0, it looks like the average rate of change is probably going to 2, is my guess, looking at that right there. And so that right there is my guess for part C. And if this was like, you know, distance in meters and time in seconds, then that would be 2 meters per second is the rate of change there. So we think that's the instantaneous rate of change. So the instantaneous rate of change, remember, so let's just redefine a couple of things. Average rate of change versus instantaneous. And there's a few versions of the formula, but it's all based on the slope formula, right? Y2 minus Y1 over X2 minus X1. And one of the function versions of that looks like f of x plus h minus f of x divided by h for whatever x value we pick, and h usually we let vary to small numbers. The instantaneous version is we just take the limit of that. So it would just be the limit as h goes to 0 of f of x plus h minus f of x all over h. And so we could do that for this particular example. We can take the limit as h goes to 0 of this quotient here resolved to 2 plus h. And as h goes to 0, and all that should be left is the 2. Now, technically in limit, it's not supposed to get there, but that's the pattern that evolves. Okay, next. Questions on that one?